All right, so welcome back. So in the last video, we have looked at into the introduction of Progan, or we have understand the theory of like what it actually is. We learned about the progressively adding more like progressively creating much like uh, much complicated images, or progressively adding more layers to both the discriminator and the generator. So we have looked at about that in the last video, how we can actually progressively do that. And in this video, of course, we are going to implement that program in TensorFlow, and also we could use pre-trained program. Like there are some powerful pre-trained models that are already trained, and they are available on a website called TensorFlow. I'm going to get back to that in just like after we just walk through through this code. We are going to look at that notebook through which we could actually access pre-trained TensorFlow models, pre-trained TensorFlow program. So first, we'll go through this code first. So again, I'm going to repeat what I have said in the last video. So program is nothing but for like when we start training, so all of the changes that we are going to do is not going to be on the architectural side, but it is going to be on the like training side, how we actually train the model. So we are going to start off by like building a very, let's say, one layer generator model, one layer CNN transpose generator model, and one layer CNN discriminator model, right? And then we're going to have and then as we go on, as we train the model more and more, we are going to progressively add more layers to the both the generator and discriminator, thus increasing size of this output. So first, when we are starting, we'll only get output like 4 by 4 image, 4 by 4 by 3 by 4 by 4 by 3, and then as we go on, so, okay. So as we go on, we'll progressively and slowly, and we'll also use like the fade in function to actually slowly like increase the complexity of the model very slowly. And then we're going to use a very smooth function through which you could actually slowly increase the complexity of the model. So that is the idea of progressive GAN for better accuracy, essentially. So now let's just go through the code now first, and then after that we'll go to the pre-trained notebook. So first, I have imported these libraries that we'll be needing. So square root function, load, as array, and I mean you could, and we'll also import some more like layers, right? And then we'll go to the first function, pixel normalization, just classic normalizing these inputs. We'll square them, find the mean, and then add a very small value, get the square root, and then divide them by this L2. This will divide the mean. We'll divide the mean, and then so yeah, that is the thing. So this is just normalizing these values just so the like gradient does not escalate to a very high number. So therefore we do this pixel normalization. And then now like this is a class, so this is the main function, call function, and then the compute output shape to actually compute the output, to return the output shape of this input, or yeah, that's it. And then we also build another class for mini batch standard deviation, right? We'll perform the formula, we'll calculate the mean of this outputs, we'll subtract the mean and square the value, right? And then we'll get the mean again of yeah, we'll get this mean of this squared term, and then we'll add a very small value, get this square root of this mean to actually get the standard deviation. And then we could find the mean pixel by performing mean on this standard deviation, and then we'll get the shape, we'll get this output, right? We'll just do that, and then we could just concatenate all this both of these values, right? Inputs and the outputs, and we could return this combined concatenated version of this matrix. And then again, we'll have this compute output shape to actually get this output, right? And then like we'll have another class, the weighted sum class, which takes in like which inherits from the add uh, add class. So we'll initialize this class with the alpha equals 0, and then we can just say alpha self dot alpha equal backend dot variable. So we are essentially going to build a trainable variable that we are going to update as we go through like trading. And then we have this merge function to actually this is the main function. So what we are going to do is we are just going to subtract 1 from alpha, right? And then we're going to multiply that by inputs and plus self dot alpha into inputs of 1, and then we'll just return the output, right? As we go on, we're going to like this alpha is going to change. Thus we can intelligently figure out whether we should give more importance to this or this, right? And then we have the Wasserstein loss again, classic loss, that is we are going to use Wasserstein loss for training of this model, because of course like Wasserstein loss performs better than other losses. I have covered Wasserstein GAN in this one of the previous videos, so make sure to check that up. If check that out if you have no idea about Wasserstein GAN, so check that out too. And then after that, we have imported the basic functions that we'll be needing, and then now we could create the discriminator. So I'll create the function called add discriminator block to actually add the discriminator. So the output inputs are, we will take the old model. So as we go on through training, we are going to update this discriminator, right? So we are going to take the old discriminator, and then we're going to make some changes to it. And also we'll get number of input layers, which is 3. So the output of this GAN is going to 3, right? So that is the inputs. And now we'll have an initialization. We'll initialize of the variable using random normal and standard deviation of 0.02. And then we could actually we'll get the input shape of this model, old model's input shape, right? So we'll get the what is the old model's input shape, which is nothing going to be the input shape of this model, right? And then we'll get the last second value and dot value and multiply by 2, and we'll do that essentially to increase this because in the last like in the previous model, like, talking in this context, in the previous model, the model is going to have half of the input that we have now. So as I've told you, as we go on, as we move on, as we go on through training, we are going to increase the size of this output of generator, and thus we should also increase the size of this discriminator. So therefore we'll take this value, we'll take the input shape value and multiply everything by 2. So that is the thing. So as we are going to have a greater input, because the generator also is going to update its like update the number of layers, and thus increase the shape of this output. So therefore we'll also increase the shape of this input of this discriminator, and we can have this input layer with the shape of input shape. And then we'll have a convolutional 2D model, 128 convolutional 2D model, 1 by 1. Yeah, all classical things. And then we'll have a leaky ReLU with an alpha of 0.2, other convolutional layer, leaky ReLU, convolution again, leaky ReLU again, and then finally average pooling. And then now we'll actually create a for loop, right? So first we'll set block new equals D, and then what we'll do is we'll just say for I in range n of input layers. So we'll go through all of these input layers, all of the 3 channels, and then from all of these 3 layers, from 3 to the length of old model dot layer. So what we're essentially doing is from 3 to all of these layers of this old model, we are just going to loop through all of these layers. And then what we are going to do is we are just going to say D is equal to old model dot layers of I. So we're going to loop through every old model layer, and then we are going to pass this D input to that old model, and then we're essentially going to do that for all of the layers of this old model. And then after we get the final D, that is going to be our output, right? Got an idea, right? I'm going to go through, like, if you understand what we are doing here is old model is nothing but the model that is trained before this epoch, right? As I've told you, in progressive GAN, in Progan, we are going to increase the layers in both discriminator and generator as we go through training. So that's what we are going to do is the input shape is going to be double, because of course the GAN also changes the number of layers, not only the discriminator. So therefore the input shape doubles. So that is why we multiply by 2 here. And then as we go on, we'll reduce the output shape, and thus we'll have this old model layer. which is essentially going to be the input layer of this. No, which is essentially going to be the first layers in the last model. So essentially, we're going to perform this old model layers just to make sure that like the outputs match up, right? And then we'll use this, and then we can compile the model, right? After defining the model, we'll use model function of keras to actually create a model, and then we could compile it using Wasserstein loss, and then we'll set an optimizer with a learning rate of 0.01, and then we'll set other other parameters, other hyperparameters, right? And then we could actually have we'll perform average pooling 2D to actually downsample this value, and then we'll perform block old, right? Essentially, we're going to perform so we're going to perform the second and third layer on this downsample. So we're going to repeat this old model layers, right? Wait, I think yeah. So that is the thing. So we are going to wait a minute. So essentially, we're going to have two models, right? So we're going to have two models, and then in this model, the input will be the input image, right? We are going to take like two discriminators here. Yeah, we're going to have two discriminators here, and then yeah. So we're going to have two discriminators, and we'll perform downsampling on this image. So we are as I've told you, we learn about fade in the last video, like how fade in happens. We'll have this parameter that is going to change or increase over epochs. So what we're going to do is we're going to have these other models, right? So we're going to have two models, and slowly we'll add this second model, the importance of this second model as we go on. So that is the thing that I have wrote here. So what we'll be doing is we'll be creating another model. So we'll be performing this input image on this another model, and then we're going to perform the old model layers, and that's it. So we're going to perform the old model layers. So essentially two layers, and then we're going to carry out like weighted sum between the two, and then we're going to loop through again. We're going to loop through all of this old model layers, and then perform all these layers, and then it will be and we'll build a second discriminator. Why? Because to perform fade in, right? We'll slowly increase these. So we'll just perform interpolation. You have any idea with interpolation of two vectors, slowly converting these vectors to actually reach at a point that are similar. So we are slowly going to use this or increase this alpha value that I talked about to actually make sure that this final model, like that model one, will be given the final importance. So that is why we'll create two models like with the same losses but with different layers. So in that model 2, we are only going to have the layers of this old model. So we are essentially going to copy this old model, but in model 1 we are going to add more layers, and then slowly, because we are like outputting both of these models just to make sure that we don't directly change these outputs into like model 1, but we slowly make the change. And then we have this defined discriminator model, right? Yeah, so defined discriminator model in which we will take n blocks as the input, number of blocks, and then input shape, which is going to be 4 by 4 by 3. And then we'll perform like we'll take in the input, we'll take in the input shape, we'll perform all of these layers, we'll perform flatten and get the final output dense, right? So yeah, so we are going to taking this input, and then we'll perform all of these layers, all of these layers, and then we're going to have a model and image input and output class, and then we're going to compile this model, and then what we are going to do is we are going to append this model and model. So we are going to append both of these models, and then we'll perform a for loop n blocks number of times, and then we'll get the old model, and we'll after like okay. So this is so you might be wondering what this is, but this after getting like both of these models, model 1, model 2, what we are going to do is we are going to these are going to be the below layers after performing all of these functions. After performing all of these functions, we are going to carry out these layers, right? We're going to calculate these layers, and that is what is happening here. So as you can see here, we are going to loop through n blocks. We are going to get the old model, which is going to be the model list. So yeah, we are going to append these models, right? So we are going to append these models to the model list. So the model, we are going to get this previous value in the model list, right? And then we are going to call this function the add discriminator block on the old model. So that old model is the output to this old add discriminator block, and then I'm going to get this model and append to this models. So that is the idea. So here what we are doing is we're just taking this input shape, which is going to be the output of this layers. So we're going to take like output of this. Yeah. So sorry, this is this. So this is going to be the output of this is going to be input of this model, and then we're going to take this output, and then essentially we are going to calculate all of these values, right? And that's it. All right. So that is the idea of like that is what we are performing here. All right. And as you can see here, the model is going to take input image and output class. All right. So we're going to perform on this input image, which is going to be that, right? So we are essentially going to, it's like this is going to be the initial model, right? This is going to be the initial model, and then we're going to slowly update these models. We're going to slowly update these models and perform this model. So essentially, just like just progressive again, we're just going to carry out this logic here. And now let's get to generator block. So that is something like very very intuitive and very logical to do there. And now let's look at this add generator block. We're going to take this old model, right? And then we're going to have add normal, like max normalization. We're going to call the max normalization function, and then we're going to get the last two layers, right? So the last second layer of the old model, right? And then we're going to perform the old upsampling on this layer on this output, and then we're going to perform a CNN layer, a classic CNN layer on this upsampling output, and then we're going to perform pixel normalization, layer ReLU, like leaky ReLU, convolutional 2D again. We're going to have pixel normalization again, and then leaky ReLU, and then we're going to finally get this output image by performing convolutional layer. And then what we'll do is we'll create the first model by just creating model and old model. So the input is going to be old model's input, and the output is going to be this output image that we are going to perform, right? So see how we get this output image, right? So we're going to add this these layers, upsampling layers to this block end, which is going to be the last layers, like one of the last layer of this old model, right? We are using like the second last layer just to make sure that the shapes match up, right? So, and then we're going to perform this, and then we're going to get this output image, and we're going to create a model. So that is going to be model one. And then the second model is going to exactly be this old model, right? As you can see here, it is going to be the output of the last layer, right? So it is going to be like the last layer, and then we're going to perform so we're going to perform this last layer on this output. So as you can see here, like upsampling 2D is like, sorry, block end is the upsampling 2D. We're going to perform upsampling 2D on the output of like the last, like the second last layer of this old model. And after we get this value upsampling 2D, we are going to perform like this last layer, and then we'll perform the weighted sum, and we could just create the final. We could create the second model, and then we'll just output both of these models in a list. So that is the logic here. So it's essentially the same logic that we have obtained in the discriminator too. So we're essentially going to calculate two models for each generator and the discriminator. So we're going to have two models. One model is going to be the old version, like essentially the old model. And the next model is going to be the second model is going to be, or more precisely, model 2 is going to be all right. So we're going to model 1 is going to be the updated version. We're going to add many layers, and then model 2 is going to be the new version. Oh, sorry, the old version. Model 2 is going to be the old version. right? And then we'll create this define generated loss function. So this is going to be the initial GAN. The initial GAN is going to be this. We're going to take this input shape, input dimension, and then we're going to perform this dense layer on this input latent, right? We're going to perform this on this input latent, and then we'll reshape these values. We'll perform convolution 2D, pixel normalization, leaky ReLU, convolution 2D again, pixel normalization again, leaky ReLU again, and then final convolution layer, which is going to be we'll have 3 1x1 convolutions, and I think the output is going to be 4x4x3. So that is the it is going to be 4x4x3. And then we'll define the model. And then what we'll do is we'll create a model list of all the models that will just store all these models. Initially is going to be the list of the same model again, and then we'll just loop through this and number of blocks we need, like the number of, like I have told you in the last video, we will have the like residual connections, sorry, like fade in models, like we're going to have number of blocks, that is this variable here. And then we'll get this and then we'll get the old model, and then we'll add the generated block, we'll get the generated block, and then we'll update these models to this model list, just to make sure that like when this model runs again, we could pass the old model, I mean the previous model, to this function add generated block, such that we could add more and more layers as we go on. So that is it, like very neat and clean and very intuitive logic that we're going to use in this code. And then we're going to define the composite, right? We're going to have a discriminator and generator, like just to use both of them. So again, we'll also have model list here. So we are going to run a for loop in the length of discriminators. So yeah, G models and D models is going to be generators of I and discriminators of I, and then we'll set. So we'll first make sure that like the D model is not trainable, D model 0 is not trainable. Okay, so we'll have the first sequential layer. We will create a first model which has like the first generator and the first discriminator, and we'll compile this model using the Wasserstein loss and Adam optimizer with these hyperparameters, and then after that we'll set the D models 1 also as non-trainable, and then we'll have the second model. It's going to be sequential, and we're going to have G models 1 and D model 1 as this model, and then we'll compile this model, and then we'll add these models to this list. We'll add both model 1 and model 2 to this model list. So essentially, as we go on, we'll add wait a minute. So as we go on, we can have this new list called model list, and then we're essentially going to return this model list, which is going to have all of these G models and D models, right? Essentially, like a combination of all these G models and D models, right? So as you can see here, one thing I have forgot to tell you is that the output of defined discriminator is going to be the model list, which is going to contain like all of these models. So essentially what we're going to do is, after training of each model, right, we're going to have many models, right? So as we perform this, as we go on through training, we're going to have many models. We're going to first create a model and update the model and create a new model, copy and update the model, add more layers, and have that, we are going to have copies of many models. And if you can think about it, the output of defined discriminator function is going to be a bunch of a list of discriminator models, and the output of generator also is going to be a list of bunch of generator models. And then we're going to input all of the discriminator models and all of the generator models, right, to this composite function. And here D model 0 refers to the previous model, and D model 1 is going to refer to the second model. So we're essentially going to have pairs of models, like previous and next, or previous and current. So that is the thing going on here. So we'll loop through all of the discriminators, right, which is going to be, and then this discriminator, wait a minute, I'll just, yeah. So, and this discriminators is going to be a collection of pairs of models, model 1 and model 2, previous and after discriminator models at each time step. And then we're going to get the first model, and essentially we're going to have two models again. So this output is also going to be a model list which contains the previous and the next model. And it is actually very good and a very neat representation also. We're going to combine, essentially we're going to have two generators, the previous generator and the new generator, which is like amazing. So we'll have pairs of pairs of GANs, right? Pairs of GANs, and at each pair, at each list, or at each index, we're going to have two generator models or two GAN models. And the first GAN model is going to be the old GAN model, and the second GAN model, sorry, I think the new GAN model, right? Yeah, the new GAN model, and the second model, model 2, is going to be the old model. Essentially, we're going to have multiple pairs of this, so through which we could make training possible, right? So like we have coded this logic here, and I think like all of these implementations, like all of the implementations on the internet have this implementation, have this logic. That is why I have used this too. I have also used this, and then we could use load real samples and call that on file name, right? I don't think we haven't used any data set here, so therefore will not have any files to train on, but we could do it. Maybe I'll find something on internet. I'll probably put that in description. Just I used exclamation mark wget and call that file name, maybe on GitHub or something. You could download it, right? And then we'll just call this load function. I don't think I put that. I mean, you could write your own load function, right? And then I think I've put the load function in this previous video, maybe in the previous code. So make sure to check that out too. All right. So we'll get the array one and all that. We don't actually need that. They generate real samples again from the data set. We'll generate the latent points using this random function from from NumPy. We'll reshape this output also into n samples into latent dimension. And then we'll generate the fake samples by calling this latent inputs and use the generator model to actually predict from them. And then we'll have this function update fade in. So as you can see here, we're going to use a very clean, neat linear formula which goes from 0 to 1, right? So alpha is going to be step by float of n steps minus 1. So here step is going to be the current iteration. Yeah, current iteration, and n steps is going to be the total number of iterations the model has to carry out. So essentially, we're going to slowly increase this alpha value at each time step, and then like we'll essentially call this update fade in until like each time step. I think we have used this function here. I'll go through that in just a minute. So we'll just loop through all these models, right? All of the models that are going to be the inputs of this update fade in function, and then we'll go to all of these layers, right? And then if we have this weighted sum, if the layer is weighted sum, we're going to set the value to layer.alpha and alpha. So we're essentially going to update this alpha value, which we have used in this weighted sum function, right? So that is the thing of this update fading that I have been talking about since the beginning, right? You might have heard me about it. If you want to learn more about the intuition, please check out my last video in which I have explained everything clearly, right? At least I have tried. So, and then we'll have this training box function in which we'll have this training loop, right? I think this is the training loop. All right, let's look at this function, the training epochs, right? And then we'll calculate the bias parts. So these are going to be inputs: generator model, D model, GAN model. That GAN model is going to be like I think it is going to be out of composite function. And then data set, a number of epochs, number of batch, and fade in. We'll set it to insulate it to false. And then if you want it, you can actually set that to true while calling this function train epochs. So we'll calculate batch per epoch and then the number of steps, right? Batch per epoch into number of epochs. And then we'll have half batch. And then we'll loop through a number of steps. We'll have this, we'll perform this for n steps. And then if this fade in is true, currently it is false, but if you want to use it, if you can use it by true. If the fade in has a true value, you're going to use this function update fade in on G model, D model, and GAN model. And then we'll just essentially going to update all of these alpha values using this update fade in function. And then we'll also going to input the current iteration, right? current step and also end steps, right? And then we're going to get this real images. We'll also get this input, generate fake samples. We're going to get the fake samples, and then based on that, we'll calculate the loss, right? We'll train the models. We'll train the discriminator models first on this real and fake data. We'll make them perform on this real and fake data and update these values, and then we'll also put this Z input on these models, and we'll also train this model also, GAN model also, right? And then we could actually get this loss functions. So that is like what you like. All of these functions take place in each epoch. So yeah, that is like a lot of work for our model to do. So yeah, so we'll be found some more functions to actually scale images and summarize performances. And then here is a trained model in which we'll just essentially we'll just call this previous functions to actually, right? We'll just call this previous functions to actually train the model. So I think this is enough, right? This is enough for this video. And now I'm going to show you something else, how to use pre-trained models. I'm going to do it very fastly. So essentially, we're going to this notebook is for like using pre-trained progressive GAN. So first, we're going to install this libraries, image.io, scikit-image, and TensorFlow docs. Again, the whole credit of this notebook, not the previous one, is going to go to TensorFlow. Also a previous one, because TensorFlow is built by TensorFlow again. So like this notebook mainly create like copyright from TensorFlow. So credit to TensorFlow. So what we're going to do is we're going to use this pre-trained model from a website. Like there's a website called TF Hub. I'm not going to go through it. And this one, yeah. So in which you could use like all the models. So go to C models and like select your problem domain, whatever that is, and you could access pre-trained models by using this TensorFlow like library, and you could call load function, and like there'll be a link. You could just call that, and you could actually access that pre-trained model, and then we'll perform a bunch of things. We'll set random set to 0 just to make sure that you will get the same values, that you will get the same images that I do, right? So we're going to set seeds as that randomness is equal for you and me, right? And then we'll import TensorFlow, and then we'll also import time. We'll do a bunch of things. Import, but like they are not very important right now. So here you can actually, yeah. So we will import some of the main functions that we'll needing. Interpolate hypersphere given v1 and v2. We'll try to perform interpolation, and then display image function to actually display this image, and then we'll also create this animate function just to make sure that we can see the interpolation action. And then this is the GIF. So as you can see, this is like interpolation between vectors. So we'll essentially get like two random vectors, and then we'll pass them through Progan. We'll pass them through Progan, and then we'll get some outputs, like two outputs, and then we can actually perform interpolation between these two outputs to actually see how they change over time. So that's a very good animation that you could look up to, and also read the code, please. And then like that is how easy it is to use a pre-trained model. So just call this program that we have initialized here way above after getting it from TensorFlow, right? And you can call that, and use that on like many different things to actually see this, like get some pretty good results. Like this is the main, like this is the actual image, and this is the predicted image, right? Yeah, there are many similarities that we can see, and there is some like model is trying to do something, change something. Yeah, that's it for this video. So hope you got anything informative and good from this video. So hopefully you understand GANs. I'll probably put the code and both the code and probably some documentation for you. Check out. Yeah. Thank you for watching again, and I'll see you in the next video.